Here we have a beam hanging from two ropes tied to a common point, and we're asked to find the tension in the ropes under two conditions. One where it's just statically hanging here, and another where one of the ropes breaks. Let's take a look at the static solution. Let's start with our free body diagram. So we have mg acting straight down here, the center of mass. Over here we have a tension in the rope of F, which will break up into components. And we'll have the same thing over here. In the x direction, we see that these two forces have to equal each other, which really just tells us that F right has to equal F left if they have the same angle theta, which they do in this case. And in the y direction, summing in the forces in the y is equal to MAGY. It's not moving, it's static, so that's 0. So basically we're told the two upward acting forces, 2 F sine of theta, have to equal the one downward acting force, mg. It's in equilibrium, and we get that F is mg over 2 sine of theta. So that becomes our static solution. Now once the rope breaks, this end is going to be free to move, and we're going to experience some type of an alpha here. So we'll define our positive directions, in this case, like that. So this will be a positive x, this will be a positive y for this problem. And that's based on the motions of these things. I'm going to call this end over here A. So we can track the motion where this rope is attached, and we certainly have our center of mass at G. We can say using sum of the forces is equal to MAG, that AGX will equal F cosine of theta divided by M, and AGY will be, if we call down positive, mg minus F sine of theta over M. So that gives us two useful equations. And the third one we'll get from sum of the moments about G is equal to I G alpha. And recall, that's always valid. We don't have to worry about the rest of that. Mg doesn't generate any moment, so we have simply F sine of theta, and it's acting a distance L on 2 away, is equal to 1/12 ml squared, the I of a beam through its center, alpha, and one of these L's goes. We can multiply through by 12, and that'll get us a 6 over here, and we end up with alpha is 6F sine of theta divided by ml. So now we've got three equations and a family of unknowns here. We don't know F, we don't know alpha, so we need to mix these together, and we know that the relationship between these is through a relative acceleration equation. So step 3 then will be to write the acceleration of G is the acceleration of A plus the acceleration of G with respect to A, done vectorially. AG, we have two values here. We have our AGX and our AGY, and they're known. We haven't really looked at AA yet, but we can think about it. Since it's tied to a rope up here, its acceleration would have to be like this. And therefore there's going to be acceleration components in this direction and in that direction. If that's theta, this will be theta here. So the downward acting one will be A sub A cosine of theta, and this horizontal one will be A sub A sine of theta. So we can bring that information over to here. We have an A sub A sine of theta here, and an A sub A cosine of theta there. Now this one, G with respect to A, you draw that out. Here's A, here's G. G with respect to A, we're looking at G from here, so that's L on 2. And G with respect to A can have, as we know, if there's an alpha, that's our positive direction, it can have an R alpha type, and it could have an R omega squared type, but again it's not moving, so it just has this. So we find that this cross product will be R alpha or L on 2 alpha. And we know alpha, it's right here. So that'll be plus a downward acting L on 2 alpha. And at that point we can just write out the equations. We have a bunch of x equations that have to be equal to each other, and we have a bunch of y equations that have to be equal to each other. And it's really just a matter of doing the mathematics on this. Now if we look at this in the x direction, we only have two components here that have to equal each other. So we can write that out, that AGX has to equal A of A sine of theta, and AGX is F cosine of theta on M is equal to A sine of theta. So with that we have a function for AA. So the acceleration of point A will be F cosine of theta on M sine of theta. And if we look in the y direction, we have this term has to equal both of these. So let's write that out. AGY mg minus F sine of theta on M equals A of A cos of theta plus L on 2 times alpha, and alpha is 6F sine of theta on ML. And we can substitute in our value for A sub A from over here. We'll get mg minus F sine of theta over M is F cosine squared theta now, when we multiply the two cosines, over M sine of theta, plus this L at least goes here, this 2 and 6 become a 3, F sine theta over M. We can multiply through by M, and let's multiply through by sine here as well, just to clean it up and get rid of all the fractions. And we'll get mg sine of theta minus F sine squared theta is equal to F cosine squared theta plus 3F sine of theta. And that'll be squared when we multiply through by the sine over here. And if I collect my terms, I'll get mg sine of theta is equal to F sine squared theta plus F cosine squared theta, that's interesting, plus 3F sine squared theta. And here we have a sine squared and a cosine squared with a common factor of F. So that'll become F sine squared theta plus cosine squared theta, which is 1. So this is just going to become an F. So with that, we'll get our answer of F will be mg sine of theta divided by 1 plus sine squared, 3 sine squared theta, which is our solution. And if we'd like to compare these two, this would be static, and this would be the case where there's one rope. Let's use a theta of 30 degrees, and sine of 30 will be a half. So our static will be mg over 2 times a half, which will be simply mg. So we'd have an mg acting up on both sides over here, in that case. And suddenly one rope breaks, and the load's transferred to the other rope, but it also begins to accelerate. So let's see, do you think it'll be larger or smaller than mg with one rope attached? So our F1 will be mg sine of theta is a half divided by 1 plus 3, and the sine of theta is a half, and that's squared. This will be 3/4, and we add 1 plus 3/4 will give us 7/4, which we invert and multiply will give us 2/7 of mg. So it turns out it's less than, in fact it's far less than, it's less than even half of the mg value while that bar is accelerating down. So there's a way to calculate a dynamic result for this system. And with that, we have our final equations for calculating the tension in the case where there's two ropes suspending it in a static fashion, or one rope where it's dynamically swinging downward with an alpha. Thanks for watching.